Okay, let's get started. So I want to begin by talking about a problem that appeared on the homework, and it kind of appears a lot of times on the homework. We keep working through the same problem, mixing over a normal with a gamma. So I'm mixing over the scale parameter with a gamma. So anywhere I see sigma squared, I write in the denominator of that gamma. So this is our mixture model. And so hierarchically, this is sampling from gamma, plugging it in here, and getting x out of it. And on average, it does something. How do we mathematically average over everything? We integrate. How do we do it on a computer? We run it in a for loop. It's a kind of a beautiful thing that happens. So the x's I get from sampling out of model proportional to this is going to be some distribution that's not normal, and it's not going to be gamma. It's going to be some averaging over those two things, specifically averaging over the scale parameter. So we've seen this a whole bunch of times, and I've asked questions like, what's alpha and beta gotta be for this to be Cauchy? And there's a couple answers to this that are pretty typical on the homework, and I usually leave this as a dangling point. I'm always tempted to clear up this on the homework, but I'd like you to think about it for a little bit. And so let's just work through this. We can see that this integral right here, integrate between 0 and infinity, can be simplified to gamma alpha plus 1/2 minus 1. So I combine the two gammas. I'll find the exponential term. E to the minus gamma x minus mu squared over 2 sigma squared plus beta. Gamma. And now I recognize this whole thing as the kernel of a density, gamma density function. This is gamma. Alpha plus 1/2. And this is a gamma with x minus mu squared over 2 sigma squared plus beta. And so I know what this integrates to, because I know what the inverse of a gamma's normalizing constant is. If I had the normalizing constant in there, it would integrate to 1, so it integrates to the inverse normalizing constant. This will look like this, gamma to the alpha plus 1/2 over this thing raised to that thing. X minus mu squared over 2 sigma squared plus beta raised to the alpha plus 1/2. And so we're almost done with this. We'll notice that this is a constant. And I've been writing everything down up to proportionality. I even chucked this just out of habit. I went from here to here because I wasn't integrating over that term. It's just a constant. Everything is fixed in here. And so this thing right here is just proportional to beta plus x minus mu squared over 2 sigma squared to the minus alpha plus 1/2. The question is what does alpha and beta need to be, maybe for this to be a Cauchy distribution? So let's just ask that question. Question, what does alpha and beta need to be for the resulting distribution? And I'll be more specific, density for this to look like a Cauchy. There's a certain amount of ambiguity in all of this. It's like, which Cauchy do I want it to look like? And so, and some of you kind of struggled with it, but some of you thought one answer makes a little bit more sense than the other one. This is the easy part. Nobody has any problem here. What does this need to be?
1/2.
1/2. Because this whole thing needs to sum to 1 for it to be Cauchy. And so, this is going to be 1/2. The question is what does beta need to be? And I saw a lot of funny things that people would do with this. A wrong answer would be, I need this thing for this to look Cauchy right here. I need this to be a 1. And so they turn beta just into 1 to do it. That would actually be a wrong answer. And so the whole problem doesn't scale that way. And so if you actually go to your simulation and you try to play around with it, you'll recognize that the degrees of freedom, while right, in here, this isn't the scale of the problem. So that would be wrong. What you really want to do is you want to divide everything by beta. So I'll just divide everything by beta, multiply by beta to the minus alpha plus 1/2, if you will. So that's exactly the same thing. And since I've been writing everything down up to proportionality, that's a proportionality constant. Just chuck that thing right here. And then the question is a little bit more clear. If I wanted the Cauchy to have the original scale of the original problem, it's winding up right there. It's already there for us. And so I think the correct answer to this, so this thing's going to be 1, and I need this thing to be the degrees of freedom that we see up there. So the degrees of freedom in the T1, this needs to be a 1. So for this to be a 1, beta has to be a 1/2. But it's kind of masking what is the scale of the problem. So some of you answered and tried to absorb beta into the scale, but if you wanted the scale to be the original scale of the problem, then you need to isolate everything right here. So a little bit of ambiguity. If you wrote down beta to the 1/2, we gave you full credit for it. If you wrote down something and you convoluted the scale of the problem, you probably figured it out while you were simulating, that things were weird. It would work depending on, if you made beta equal to 1, it wouldn't have worked. If you divided by beta and redefined the scale of your normal distribution that you were mixing over, it would have worked. But you should have recognized in that step of the problem when you went to simulating it, that you probably wanted to already have the scale modeled in the normal distribution. So it's a trivial point. It's no big deal. If you coded it all up and you understand all this, that's all I really care about. If you got marked off a 1/2 point because of this, I wouldn't really worry about it. Just take it home as there's probably a better interpretation of this problem. So if you write down alpha, beta, or both a 1/2, you did a good job. So keep in mind that if alpha and beta are both the same numbers, then on average, this thing is 1. And so what are we doing when we plug in that average right here? This thing is on average 1, so I'm not changing the scale on average. That's a good way to think about that. So that's all I want to say about that. So there might be a minus 1/2 or a, something like that, just to indicate that look at this problem again.
So you're saying that whenever we set alpha and beta, it's good to have the normal is just scaled by 1. How does that,
On average.
yeah, how does that translate into
But just think if it was exactly 1, right? Then I wouldn't have changed the whole problem. And it's just a normal distribution. But there's some noise over it in a gamma format, and it changes it from a normal to a T.
So as if you're normalizing the noise equally over in a flat shape over.
Stuff to think about. What does this integral represent to me? So, if I were going to try to add noise to a scale, I want to do it in a unbiased sort of fashion. That means multiplying by, on average, 1.
So if that's the case, wouldn't that be considered as white noise since it's just flat all over?
White noise is not well defined in all distributions, in all worlds, but nobody ever considers gamma white noise.
Yeah.
Usually we consider it normal. So not quite.
But just because it's flat over all,
It's not flat.
on average.
Yeah, but on average, it's 1, but it's certainly not flat. This shape looks like that.
Okay.
Cool. Okay, so just a tidbit, if you didn't interpret correctly what we are writing down in that problem.
Can we say that when beta equals to 1 Then the scale is 2 sigma squared.
Yeah, then it's all messed up. Yeah, then you'd square root of 2 sigma squared. And you could simulate it like that, and it probably turned out fine. And so you understand how these two levers are working, and they're not well identified unless you say you want the scale to be a specific thing. And so which scale would you want it to be? Because there's infinite many solutions. I think there's one answer that appeals to us a little bit more. But the other ones, if you did that, you would be technically right that you could induce a Cauchy out of it. So, but what do most people usually do with it? They want this thing to be on average 1 that you're multiplying by and preserve the original scale. So from a mathematical point, no problem with your answer. From a statistical interpretation point, it could be a little bit better. Does that make sense? Okay. On a test, to rule out ambiguity, sometimes I like ambiguities and unknowns. So I know it takes you time to shuffle through it, but I think there's value to that. On a test, I would always be very specific to what I was looking for. Okay, my favorite topic of all time, hypothesis testing. So, what do you guys think? Pretty useful stuff, right? The savior of all statistical analyses, how to test. So no controversy whatsoever. I want to know if something's true. Statistics gives us the power to determine that. Right? You guys think? I'm the professor, so I get some say over this, but maybe you all feel differently. Anybody want to say anything about that? No problems with statistics these days. Everybody loves everything we do. So this is the most contentious area of all of stats. And so this is what I consider the black eye of statistics. I don't think there's I think that there's some answers out there that are fairly absurd. And I think that there's some answers out there that are hard to understand, but they make a little bit more sense. We have to understand what it means to actually test something in the first place and be specific about what it means to test. So all these different groups that are running around and they disagree with each other are not being specific in what they mean by testing something. And so I'll say more about that as we go through all of this. So this is just kind of an introductory lecture into this, and over the next couple lectures we'll get more and more into it. We'll probably do this for about a week and a half, because I think this is important. I did post a paper online that you can read through. The example that I'm going to be showing you comes from this paper. It's from Mark Shervish over at Carnegie Mellon University. This is a terrific paper. You can just click on that. I called it the p-value paper. Here it is. So p-values, what they are and what they are not. He tries to interpret these things for you, and he considers 3 types of tests. So you can go through all the details, his citations. If you're not familiar with likelihood ratio testing, he'll cover this with citations. If you want to see more on likelihood ratio testing and where these different test metrics come from, you should take a formal class on inference. 5114. But I'm going to be showing you some p-values that get computed. And if you want to know more about this, it's right here. So let's just back out, and I'll tell you what Mark says. He's also written a supplementary paper called Bayes factors, what they are and what they are not. So you might think Bayes can solve all problems. And he shows some issues that can happen with Bayes factors. In fact, his point of trivia, my advisor read Mark Shervish's paper. I think he was an associate professor at the time, and said the same thing can happen with some types of Bayes factors, and wrote him a note about it. So Mark Shervish published that paper and put my advisor on it. And so just keep in mind that all forms of testing, there's something to be said about them. Okay, so let's just consider 3 types of tests. Okay, consider a parameter. A 1-dimensional parameter. Let's just call it theta. There are three types of hypothesis tests. Concerning theta. In two of these, you're very well equipped with, at least in a testing situation, a actual midterm type situation on how to answer. So probably your stat professors before me have disciplined you so hard in how to answer these questions that it's automatic. So here's one such test. Theta is equal to theta naught. Okay. We write that a little bit differently. H naught, theta, is equal to theta naught. Okay, so what this says is the null hypothesis. Our hypothesis that we start with is that theta is equal to some value. And we want to ascertain whether or not it's true. Okay. This just says null hypothesis. If this isn't true, then you're likely to think that the alternative is true, the complement of that thing. Statisticians usually warn you not to confound fail to reject with acceptance. I don't really care how you phrase that. You're going to do something with this at the end of the day. And so statisticians have all kinds of quirky language to say, I didn't say that. You know, I didn't say go and accept the other thing. I just said that, you know, the evidence suggests that that one's not true. And say the complement was true. And so it gets very confusing. Okay, there's another type of test. Oh, and I'll say this is called the point test. Some people call it the sharp test. Or some people call it the simple test. And this would be versus, if we're talking about the complement, the simple versus compound test. I'll say complex. This is simple, a point, and the not simple thing, compound, complex thing, be an interval. Everything but that point. I usually either say one of these two things. Some people call it the two-sided test, and I really take issue with that language. That's certainly geared up for Stat 101 students to learn an algorithm for testing. So, but yeah, in Stat 101 classes, we usually confront this test with a two-tailed test. Test how much mass is in a couple tails of the distribution. Okay. Another test would be theta is greater or equal to theta naught, or you could say flip the direction. Theta less than theta naught. It's usually called the one-sided test, and I don't really have a big problem with that because you are testing on just one side. This is a little bit different because you're trying to test this point, but you have a mechanism for addressing how much mass is in two tails and you add them up. So this is maybe the one-sided test. And then there's an obvious third test in here. Theta is an element of two endpoints. So I'll say this is theta 1, theta 2. And this would be aptly called the interval test. So three things that I can determine from this. I want to point out that these two tests are limits of this test. Should be, if we get the right mathematics. That if I extend one of the endpoints out to infinity or negative infinity, then that should be the one-tailed test. And if I collapse theta 1 and theta 2 onto each other, that should be the point test. So, you guys know how to test this in general? I haven't been too specific about what my distribution is, but can somebody help me out? What do you do? let's imagine that the data that we had was normally distributed data, and theta was mu. Okay, so let's just write down a concrete example. Say I got some data from a normal distribution with parameter theta in here. And I'll say it has variance 1 and it just happens to be known. Okay, so hands of statistical gods came down and saved the day because they only gave me one data point. So if I wanted to test this, how would I do it? Yeah, significance level, so you would probably select alpha is equal to something, so this is your type 1 error. You'd probably pick 0.05 because somebody told you. What's so special about 0.05? Anybody that's taken one of my classes has heard me say this before. I guarantee it's the reason. So Fisher said in one of his seminal texts that 1 in 20 is a clear indication that something's off. That is 5% of the time. We wouldn't expect for something like that to happen. So we kind of threw that out. We've been going with that for a long time because Fisher said, but why did Fisher pick 0.05, do you think? Why has everybody said that's pretty reasonable? Why is 0.06 not a great number? Yeah, it really is because we count in base 10. And so if we had 6 digits on our hand and we counted in base 12, all the significance level thresholds would have changed. And so a lot of decisions out in the universe would have changed. I'm going to suspect that all of those scientists would have cherry-picked their data in just the right way to get their p-values just right. And so that's a major critical error of hypothesis testing, is this sort of arbitrary thresholding, saying that if you're going to program something up on a computer, you're going to need to do something to make a decision. So anyway, 0.05 happens for fairly arbitrary reasons, and I'm always kind of enamored by how many things are controlled by the fact that we count in base 10. Okay. Anyway, Daniel says he knows how to do this. So undergraduate, he can do this in his sleep, 0.05. Then what do we do?
You can calculate probability, which means p-value, or you can
I compute a p-value, so I end up computing the p-value for x. And so I end up integrating over my distribution, right, in some direction. So what distribution am I looking at? It's a normal distribution. It's centered at theta naught. So this is my null hypothesis. So I end up conditioning on the null distribution. It's a normal distribution. A lot of times you're not so lucky that your data is normally distributed. So a very common sort of thing that statisticians will do is they'll average a whole bunch of stuff together and invoke the central limit theorem and talk about population averages. I've given you a new tool where you can separate out populations and learn about group averages. And so with the computer, we can do fancier things. But let's just go back to our 101 classes, understand what we do. We get our null distribution. Variance is easy, so it's just 1 in this case. There's only one data point. I can do this with multiple data points. It's just going to scale my variance by n. So really just don't want to touch that. So we just do this with one data point. And then you end up looking at your critical thresholds. This is going to be 0.025 right here. This is how much area is in here. This is going to be 0.025 right here, how much area is in there. We compute these interval thresholds right here that have that much area. So we've calibrated this to our specific variance, and then we look at where x is. And so We compute if x is in here. We compute if it's out of there. And so in the strict Neyman-Pearsonian testing, they don't really care what the p-value is. They want to know if the value is in here or out. So if x is out here very far, the p-value is going to get smaller and smaller and smaller. So, and that happens on both sides. So that's the typical sort of thing. And how do you do that? You end up looking at a CDF function, and you end up looking to see if x minus theta, absolute value, so is less than. So I end up computing this thing right here. Theta naught I plug in, our null. And then I check to see what is this value. If smaller than 0.05, so this is my p-value. If smaller than alpha, we reject. I'm trying to write this as confusing as possible on the board because usually that's how Stat 101 students are presented this for the first time. And then the teacher will say something like, that's exactly the same procedure, checking to see if things are in or out of this interval. There's a one-to-one correspondence between those things. And then they'll tell you that they just taught you about confidence intervals too, and this is what you do. And so this is what you do. Again, what Daniel just told us is we specify our significance level. Then we compute our test statistic. In our case, it's just x. Then we compute our corresponding p-value when we make a decision. So they teach you an algorithm. And they teach you this algorithm for a whole bunch of different situations. And they see if you reject appropriately or not. And if you say it in just the right way. So they'll ask you to interpret this confidence interval, and if you interpret it wrong, they'll say, what's the probability of theta being in the interval? And you'll say, I can't answer questions like that. I'm supposed to say that's unanswerable. However, I can talk about the probability of my random interval covering my true fixed parameter. So if you say it just a little bit wrong, you lose 50% credit on the test, and you can't go on to be a statistician.
Wasn't that confidence versus credibility discussion?
Well, so we had that a long time ago, and if I give you the magic ability to be a Bayesian, then you can tell your Stat 101 teacher they're wrong about all things. So you get to go back now. They will love this. If you're a Bayesian and you have different ways of interpreting things, you might not get the coverage thing right, depending on which prior you use. However, it's pretty uncommon for your confidence intervals to cover at the levels that you say that they're covering at, 95%. You need to check that. In this trivial problem, this interval that you would construct would cover at 95%. There's no asymptotic anything, just because I gave you normality up front. Okay, so that's about what we do. If I ended up asking you to compute a p-value for this one, you would have drawn the same null distribution, centered at theta naught, and then I would check how much area there was to one of the sides. I wouldn't do both sides. And so I'd end up checking this level 0.05 and seeing if my data point was in this extreme region or the less extreme region. So with respect to the null hypothesis. And this side would change according to the sign right there. So which directions do you go? You chase the alternative tail direction. That's always true. Okay. What about the interval test? Before we answer this question, what is the interval test and how does a non-Bayesian confront this test? Because everything Daniel just told us and everything I asked about was specific to non-Bayesian testing, classical testing. How are these two tests derived? Daniel gave us testing procedures that did something mathematically. And so I can come up with any testing procedures that I want. I can draw a random number between 0 and 1, and if it lies below alpha, I can say reject. There's my testing procedure. I didn't look at your data. I didn't care what your hypothesis was. And so Daniel's testing procedure does something a little bit better than what I just described. Let me say it again. So I can come up with an arbitrary testing procedure. You come to me with data, same data that Daniel gets to see, and I compute a random number between 0 and 1. And if it falls below alpha, the type 1 error, then I reject. Daniel's going to compute a p-value, and he gave us a mechanism for doing it using the CDF of normal. And he's going to see if that number ducks alpha, and he's going to reject accordingly. He has type 1 error, 0.05. What is the type 1 error of my procedure? I just draw a random uniform. Does anybody know the answer? The null is true and I reject it. So I've conditioned on the null. That's what Daniel did. I didn't really do anything with it. And Daniel's going to condition on the null, compute a p-value, and see if it ducks alpha. So he's computed some random variable, this p-value thing. Does anybody know how it's distributed under the null? It's uniform. And so that's what gives Daniel's thing the ability to reject with type 1 error, 0.05. It's just a uniform random number. His calculation is a little bit more sophisticated. He's controlling for what happens in the alternative space, possibly really well or really poorly. But he's considering something else. So we're both generating uniform random numbers under the null. So turns out Daniel's procedure has more power. His type 2 error is lower, where my type 2 error turns out to be 1 minus alpha, as high as you could get. You couldn't do any worse. So Daniel gave us a procedure. And what I just said is his procedure minimizes the type 2 error. So I'm just going to write this down. The procedure Daniel, and I'll tell you who Daniel got this procedure from. Had type 1 error, alpha, and minimized the type 2 error. This is if the alternative is true, did you reject appropriately? If you didn't, that's type 2 error. Type 1 error considers if the null were true. So if the null were true and I failed to reject, I did the right thing. So if the null were true and I rejected, I did the wrong thing. And similarly with the alternative, I can either make a right decision or a wrong decision. And those are controlled by 2 different error rates. And in typical statistical testing, we fix this and we try to minimize that. Now, you can already say, I have a huge issue with that alone. And we can talk about the reasons why that's done. But usually, our null is on the thing we consider a little bit more. So we have full control over that error rate. Okay, what is this called? Daniel didn't come up with this for the first time, I can assure you. But he's remembered it well. Who gave us this? Minimizing the type 2 error rate. So this is an optimization procedure. What Daniel told us did do this appropriately, I can guarantee you, because when I was in grad school, I proved that. The way you did it was optimal. This is Neyman and Pearson. So this is what the Neyman-Pearson limit is all about. Which Pearson? Which one? Egon. Yeah, it's the sun. So I want to take you back to quite a few months ago when we talked about some disagreement between Fisher and Neyman and Pearson. There's a little bit of history involved in this. So Fisher came up with the idea of computing a p-value. And he's also the first one that I can find that ended up saying, at least in print, 0.05 is the right number in threshold. Then Fisher kind of went on to say, well, p-values that are like 0.06 are pretty close to 0.05, so maybe we should think more carefully about this. So Fisher didn't want to do strict thresholding. And he started advocating not doing it and using some common sense. And Fisher was a scientist. He wasn't a mathematician per se. He had excellent mathematical abilities, but he was studying problems in genetics and biology, and so in agriculture. And so he kind of was thinking like a scientist and thought, well, you know, if I get a p-value that's 0.051 and a p-value that's 0.049, aren't those about the same thing? And you can let those decimal places roll if you want to get them even closer to each other. And so he had kind of a problem with it. Neyman and Pearson came in. So this is baby Pearson. His father, Carl Pearson, years previous, had had quite a few disputes with Fisher. And so they were head honchos and they would fight with each other. Very typical of academics back then. And baby Pearson got together with Neyman, who's a mathematician over at UC Berkeley, and said, hey, let's formalize what Fisher just said and tell how to compute a p-value such that we fix the type 1 error rate and minimize the type 2. I can minimize the type 2. I can bring it down to 0 by bringing the type 1 all the way to 1, and vice versa. And so it's kind of like if you have a spam filter or something like that. If I declare everything spam, I call all my spams. But I have a horrible error rate on the other side. If I let the floodgates open and I catch no spams, I drive that down. At least all my real email came through to me, but I didn't catch any spams. So I have an error rate of 0 on one of those two sides.
So, because I'm not as familiar, there's a type 1 and type 2 error. We're talking about precision and recall.
Yes. So they can be calibrated to each other. So precision and recall aren't the same things, but if you tell me n, I can compute one from the other. And so, but they are slightly different things. Let me come in with formal definitions and write down exactly what they are. So, but that's how computer scientists usually calibrate over to this stuff. And so it's the same sort of thing. So precision is make sure the things you got are true, but make sure that you're getting all the other things that are true. And so the denominators in those spaces are a little bit different. But yeah, they can be calibrated and they're considered for the exact same reason. Okay, so this is Neyman and Pearson, and Neyman and Pearson gave us a mathematical way to solve this problem. And so if you've taken an inference class and seen the Neyman-Pearson lemma, they explain how to do this optimization. Does anybody know how to do it? We're going to start revoking qualifying exam passes pretty soon. I know you guys know. Come on, help me out, senior stats student.
Likelihood ratio test.
That's it. So, Neyman-Pearson lemma. So, Pearson lemma says likelihood ratio test so what this is I end up maximizing over the null space, theta in the null. I look at my likelihood function and I divide by the maximum over the entire theta space. There's different ways to do it. Some people will put the alternative down here. Some people will put the union of both spaces. I hope you can recognize those are one-to-one mappings with each other. So one of these numbers lives between 0 and 1, and one of them lives between 0 and anything. But I'll put it over the whole space so that this number lives between 0 and 1. So it turns out solving this problem in which test statistic in ranges of those test statistics with respect to the data gives us the solution to this problem. So working through this is a test statistic. And this test statistic will encode all of this. So if I threshold this test statistic by a particular error rate, so I pick the test statistic that corresponds to a particular error rate, this is equivalent to that. There's a proof. that says that. That's kind of a neat thing. If I were Naaman and Pearson, I'd be incredibly impressed with myself for coming up with all that. Saying that, I hate it. You know, I cannot use this stuff. And so, and there's some severe problems with it. There are some p-values that I like that are better than others. So p-values say the distribution of more extreme data than your observed data under the null hypothesis. Which distribution are we using to describe more extremity? It's going to be derived by the test statistic that we get from this thing. So that's a function of the data and the null hypothesis, and it'll tell us how far the data needs to deviate from the null before we want to reject it. It turns out thresholding that test statistic has some pretty nice properties. Okay. Turns out when this test statistic is monotone, we don't have a big disagreement on how you use it. But you can imagine if this function is not monotone, things become a little bit blurry on how we use this test statistic. More extremity doesn't mean the same thing to us. That's a very technical thing. I didn't cover it in great detail in my stat inference class. I'll leave that for a more advanced stat inference class, but if you take advanced inference, they'll tell you about those monotonicity properties and why they're so important. So people that are computing p-values using these test statistics and the distributions that they induce, if that function is monotone, I'll probably agree with your inference. I'll probably think it's about fine. And if not, then I'll probably have lots of gripes and questions, and there'll be lots of disagreement out there in the universe. Okay, so
you're saying that if it's not monotone, you need to compute something like the second derivative to know where you stand because things are broken.
here's my take. If it's not monotone, you shouldn't be using them. That's my position. So, saying that, there is a very interesting culprit on the board. This one and this one. There's two that will not induce monotone like the new ratio test. So, this one's probably the more common one that people use. This one is okay. This one has monotone like the new ratio test. So I'm telling you guys a lot of information to tell you that the thing that Mark Shervich derived for us and wrote down, this actually comes from Eric Lehman's book. He has no relationship to me. He has an H in his name and an extra N in his name. But he had derived this. So the interval test, the p-value corresponding to it, and I'll write it down like this. X, I'll write down theta 1 and theta 2. Those are part of my hypothesis space. This ends up looking like this. Theta x minus theta 1. Sorry, this is phi, cap phi. So this is the CDF, the normal. This is specific to our example with the normal data. Plus phi. X minus theta 2. This has a condition if x is less than or equal to u bar. So that's just mu1 plus mu2 over 2. Easy to discern. If that's not true, you flip these things around. I arbitrarily assign the equal sign because the probability on that part of the space is 0. So it doesn't matter which way you put it. Okay, let me just draw you a quick picture. If this is true, so this is just this condition that I'm looking at something. I have theta 1, I have theta 2. Oh, sorry. Let's call that theta bar. Quickly, notation can change. So I've got these things right here. I've got theta bar right in the middle. And I'm just checking to see which x everything is closer to. What this test really does is it checks to see how close you are to the endpoints, which is maybe a good proxy for a test, but this is the one that's induced from the Neyman-Pearson limit. And so this is just going to be some CDF right here. I'm going to check against theta 1. So this thing is centered at theta 1. This is x. This is all of my data right here. This is going to be another normal distribution. And this is going to be theta 2. I'm going to have some x. I'll have like theta 2 right here. Sorry, theta 2 is going to center this. This thing's going to be negative, and I'm just going to be adding together that area. So what this test actually is you're just testing the endpoints and adding together those two corresponding p-values. And Lehman, Mark Shervish tell us mathematically this might be okay. We don't see this test pop up too often, but I want to point out that if theta 2 ran off to infinity, that we have terms dropping out of this. One of these would go to 0, one of them would go to 1. If theta 1, sorry, I should have, theta 2 ran off to infinity, those CDFs are going to be dropping to 0. So this one right here, this thing would go way over here. That would actually sum to 1 right here, and this thing would sum to 0. This would be 0. And so this would limit to the one-sided test. And I want you to also notice that if theta 1 and theta 2 are the same numbers, we're going to get 2 times that corresponding CDF. And in that two-tail test that I don't like the name of, we add together those tail masses twice. And so this actually limits to the one-tail test as well. You can verify all that, and Mark Shervish walks you through that in his paper. So this is not just any old test. This is the one that they say is uniformly most powerful, i.e. under all data conditions, it minimizes the type 2 error rate for a fixed type 1 error rate. So I want to show you an example, just real quickly. Consider this example. X is equal to 2.18. Get some numbers real quick. We'll see how this thing works. And I want to test theta element of minus 0.5 to 0.5. Now, I don't know how to do this in my head because I can't integrate over normal CDFs, but my computer can do it just fine. So I want to compute this p-value. Okay, my computer's out of batteries, but I was thoughtful enough to write this down. I know the number. So the p-value for this, I wanted you to see the computer actually computing it so that you got convinced I didn't just make these numbers up. But this is 0.0502. These numbers appear in Shervish's paper as well, and he computed them correctly, and I confirmed. And so this is a clear fail to reject. This is the reason he picks these numbers, so he picked them fairly arbitrarily. And he said, what if you're just right on the threshold? This is a different contentious question. Neyman and Pearson say fail to reject, that's all there is to it. So this is a yes-no question. This is not what Fisher's talking about. This is why they got into a big fight over it. There's some other numbers. This one's a little bit more interesting. This is why you might want me to confirm that I've computed everything correctly, but you can confirm it at home. I want you to compute theta in minus 0.82 to 0.52. Now this is very important. This interval lives completely inside of this interval. My question is should this p-value get bigger or smaller? The corresponding p-value.
Should be harder to reject.
So be bigger or smaller? I'll tell you what the answer is and we'll conclude. But what do you guys think just before we do this?
Larger interval means should be harder to reject, right? The p-value should be larger.
Maybe. So maybe bigger. So what do you guys think? Ben's usually right. So larger interval should correspond to maybe bigger p-value. That's what he says. I think bigger interval, so long as they're within this thing, this other thing is right within it, that's important, should mean, yeah, that measure of support should get larger. Think about if that interval was infinitely big. So what should the p-value be? Probably be 1. So
But
it's supposed to be,
isn't it further away now though from the x value? So
yeah,
it's
so
gonna
now
be-
you're doing, now you're staring at this.
Yeah.
You're computing. So Ben did something different and he thought about logic. And Tessa did something and she looked at this and was able to figure out that my x was very, very far apart from my other thing and thinks that this function, because she's so good at doing this math in her head, maybe could have gotten smaller. It turns out it was 0.0498. It got smaller. Here's the kicker. And I'll show you this all on Wednesday when we come back around to this, that when this number starts to shrink towards minus 0.52 but not getting there, this number will start to also get bigger. It'll do something non-monotone. And Tessa could have probably told us that. This is a train wreck. And this shows us the importance of that monotonicity. We're going to come back and talk about all of these issues, which p-values I will tolerate, some of them that I think you probably should stop calculating, but I won't be compulsory about it. You're allowed to decide for yourself. But at least we need to understand this. Then I'm going to show you how Bayesian addresses all of this, and you can decide whether or not that's satisfactory. I'll see you guys on Monday for the exam. So good luck studying. Sierra will have all the videos to me in a couple minutes, and I'll spend the afternoon making sure they all show up. Homework. Yes.